The universe is 13.8 billion years old, but it's already 93 billion light-years across. That's a staggering 93 billion light-years across. This isn't a trick of perspective or a miscalculation. It's a profound consequence of the universe's relentless expansion, a phenomenon that has reshaped our understanding of cosmic distances and time. For centuries, humanity has gazed at the stars, believing what we saw was a static snapshot of the cosmos. Ancient Greek astronomers, like Claudius Ptolemy, placed Earth at the center of a celestial sphere, with stars fixed on its outermost shell. This geocentric model, though incorrect, was a testament to humanity's early attempts to rationalize the seemingly unchanging heavens. Even Nicholas Copernicus, who famously shifted Earth from the center of the solar system in the 16th century, still envisioned a universe with a fixed, unmoving sphere of stars. It wasn't until the early 20th century that this static view of the universe began to unravel, replaced by a dynamic, ever-evolving cosmos that continues to surprise us. The first crack in the static universe model emerged from the theoretical work of Albert Einstein. In 1915, his general theory of relativity revolutionized our understanding of gravity, describing it not as a force, but as a curvature of space-time caused by mass and energy. When Einstein applied his equations to the universe as a whole, they predicted a dynamic cosmos, one that must either be expanding or contracting. Uncomfortable with this implication, Einstein introduced a cosmological constant into his equations, a fudge factor designed to maintain a static universe. He would later call this his biggest blunder, as observational evidence soon confirmed the universe was indeed expanding. The observational breakthrough came primarily from the work of American astronomer Edwin Hubble. Beginning in the 1920s, Hubble, working at the Mount Wilson Observatory, made groundbreaking observations of distant galaxies. He used the powerful Hooker telescope to measure the distances to these galaxies and, crucially, their velocities relative to Earth. By analyzing the light emitted from these galaxies, Hubble observed a phenomenon known as redshift. Just as the pitch of a siren drops as an ambulance moves away from you, the light waves from objects moving away from us are stretched, shifting towards the red end of the electromagnetic spectrum. The greater the redshift, the faster the object is receding. Hubble's meticulous measurements revealed a startling correlation. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided the first compelling observational evidence for an expanding universe. It wasn't that galaxies were moving through space, but rather that space itself was expanding, carrying the galaxies along for the ride, much like raisins embedded in a rising loaf of bread. This discovery fundamentally changed our perception of the cosmos, transforming it from a static backdrop to a vibrant, evolving entity. So, if the universe is expanding, how does that explain the seemingly impossible size of the observable universe? Imagine a tiny ant crawling on the surface of an inflating balloon. As the balloon expands, the distance between the ant and any other point on the balloon increases, even if the ant itself isn't actively moving across the surface. In a similar way, as light from a distant galaxy travels towards us, the space between us and that galaxy is continuously stretching. This means that by the time the light reaches our telescopes, the galaxy that emitted it is now much, much farther away than it was when the light first began its journey. Consider a photon of light emitted from a galaxy 13.7 billion years ago, just after the Big Bang. In a static universe, that photon would have traveled 13.7 billion light-years to reach us, and the galaxy would still be 13.7 billion light-years away. But in an expanding universe, as that photon journeyed across the cosmos, the fabric of space-time itself was stretching. This stretching effectively increased the distance the photon had to cover, and simultaneously moved the source galaxy further away from its original position relative to us. By the time that photon finally arrives at Earth, the galaxy that emitted it could be an astonishing 46.5 billion light-years away. This is the current estimated radius of our observable universe, a sphere centered on Earth, encompassing all the light that has had time to reach us since the Big Bang. The concept of an expanding universe also gives rise to the idea of a cosmic horizon. Just as the Earth's horizon limits how far we can see due to the planet's curvature, the cosmic horizon limits how far we can see due to the finite age of the universe and the finite speed of light. We can only observe light from objects whose photons have had enough time to travel to us since the Big Bang. Anything beyond this horizon, no matter how bright or massive, remains forever hidden from our view because its light simply hasn't reached us yet. This doesn't mean there's nothing beyond our observable universe. It simply means we can't see it. The universe as a whole is likely much, much larger than the portion we can currently observe, possibly even infinite. The expansion of the universe isn't constant, it's accelerating. This astonishing discovery, made in the late 1990s by two independent teams of astronomers studying distant supernovae, earned them the Nobel Prize in Physics in 2011. Supernovae, particularly Type I supernovae, are incredibly luminous stellar explosions that serve as standard candles. Their intrinsic brightness is known, allowing astronomers to calculate their distances from Earth. By observing these distant cosmic beacons, researchers found that the expansion of the universe is not slowing down due to gravity, as was previously expected, but is instead speeding up. This accelerated expansion implies the existence of a mysterious force counteracting gravity, pushing galaxies apart at an ever-increasing rate. Scientists have dubbed this enigmatic force dark energy. While its exact nature remains one of the greatest unsolved mysteries in physics, dark energy is thought to comprise about 68% of the total mass energy of the universe, dwarfing the contributions of ordinary matter, the stuff we're made of, and even dark matter, another invisible component that interacts gravitationally, but doesn't emit or absorb light. Understanding dark energy is crucial to comprehending the ultimate fate of the universe. Will it continue to expand indefinitely, leading to a cold, desolate Big Freeze? Or could dark energy eventually dissipate, allowing gravity to reassert itself and trigger a big crunch? The answers remain elusive, but ongoing research, including missions like the European Space Agency's Euclid telescope, are dedicated to mapping the large-scale structure of the universe and shedding light on the nature of dark energy. The implications of an expanding, accelerating universe are profound. It means that the galaxies we observe today are not only farther away than their light travel time suggests, but they are also receding from us at ever-increasing speeds. In fact, many distant galaxies are already moving away from us faster than the speed of light. This isn't a violation of Einstein's theory of special relativity, which states that nothing can move through space faster than light. Instead, it's the space between us and those galaxies that is expanding faster than light, carrying the galaxies along with it. This means that over vast cosmic timescales, some galaxies will eventually recede beyond our cosmic horizon, their light forever unable to reach us, making them permanently invisible to future observers. Our observable universe is, in a sense, shrinking over time, not in physical size, but in the number of galaxies whose light we can ever hope to detect. The concept of cosmic expansion also helps us understand the cosmic microwave background, CMB, radiation, often called the afterglow of the Big Bang. This faint, uniform glow of microwave radiation permeates the entire universe and is considered one of the strongest pieces of evidence for the Big Bang theory. The CMB is essentially the oldest light in the universe, emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine and form neutral atoms. Before this epoch, the universe was a hot, dense plasma, opaque to light. As the universe expanded, this ancient light was stretched and cooled, shifting from visible light to the microwave portion of the electromagnetic spectrum. Observing the CMB allows us to peer back in time to a very early stage of the universe's evolution, offering invaluable insights into its initial conditions and subsequent development. Missions like NASA's WMAP and ESA's Planck satellite have meticulously mapped the CMB, revealing tiny temperature fluctuations that correspond to the seeds of the large-scale structures we see in the universe today, such as galaxies and galaxy clusters. So, the next time you gaze up at the night sky, remember that you're not just looking at stars and galaxies as they are right now. You're looking back in time, witnessing light that has traveled across an ever-expanding cosmos, a journey that has stretched both the light itself and the very fabric of space-time. The universe is a dynamic, evolving entity, far more complex and awe-inspiring than our ancestors could have ever imagined. And the deeper we look, the more questions arise, pushing the boundaries of our knowledge and inspiring the next generation of scientists to unravel the universe's profound mysteries. What new discoveries await us as we continue to explore the edges of our observable universe and beyond?